Hi, guys. Okay, so let's look at the exercise problems from chapter 12, Intermolecular Forces. So please make a note of one thing. Sections 1, 2, 3, 4, 5, these are on matter which we have discussed earlier in this course, early in the semester. So those parts, you can just watch the videos on that and take notes. You're going to leave sections 7 and 8, which deals with the structure of solids and then the phase diagrams, which is beyond the course for like Chem 30A and Chem 92. So anyway, so now our focus here is on intermolecular forces. So we know that there are the intermolecular forces. There is a dipole-dipole force. There is London dispersions, London dispersion, and then we're going to look at the hydrogen bonding. So these intermolecular forces influence the properties of the molecules, boiling point, melting point, whether they exist in solid, liquid, gas, and like whether they will have a lower density, higher density, or well, they're going to expand when they're going to, like when they're frozen. So will they expand? Or so those things. So these properties are influenced by the specific intermolecular forces. So in the molecules. Now keep this in mind. That one thing, London dispersion forces, LDF, or these are also some of the books call them dispersion forces. They are the same in all the molecules. All the molecules have London dispersion forces. Now the only thing is next is dipole-dipole and hydrogen bonding. So here we are given this question number 12.6.1, and this is from the section on the intermolecular forces here. Arrange the following in the order of decreasing boiling point. Okay, so you are given carbon tetrafluoride. This is methyl ethyl sulfide, dimethyl sulfoxide, and methyl butane. Now here's the deal. You guys in Chem 30A or Chem 192 or similar courses, you guys do not have, like, we have not taught you about organic chemistry, drawing their structures of organic chemistry or their names and so forth. So don't worry about it. Right now, these are the structures of these molecules. Carbon tetrafluoride, ethyl methyl sulfide, dimethyl sulfoxide, and then this one is the 2-methyl butane. So these are given to you. Now, how do you identify the boiling point? So what are the things that influence the boiling point? The things that influence the boiling point is, of course, so the London dispersion forces or the hydrogen bonding or dipole-dipole, what of those are present here? So one thing is there, after you get the structures, see, for homeworks and all, you can get them from Google. So that's one thing you can get. Okay, so this one has London dispersion forces, all of them. So what is a London dispersion forces? London dispersion forces are just the spread of the electron cloud. See, all of them are basically clouds of electrons. And these are like these clouds of electrons are spread out in a certain way. Either they are confined like in a ball formation, like from outside, they will look like the molecules would look like a ball, or they're going to look like those tubes, like rods, like mattresses, like that feel from outside. The look is like that. Okay, so that's one thing. So all of them have London dispersion forces. Next is we are looking at the decreasing boiling point. So out of that, now boiling point is when a liquid is being converted to a gas. Okay, liquid is being converted to a gas. So liquid, the particles are close comparatively, like not very close, but more mobile. But gases, the particles are very far away. So you need a lot of energy to break away what is binding these particles in the liquid together. And that energy, then when that, what is that attractive force in the liquids that's keeping them together? So if you identify that attractive force, so is it a dipole-dipole or hydrogen bonding? So clearly this molecule for the hydrogen bonding, it's always the oxygen and the hydrogen that is attached. Next is if there is a hydrogen attached to nitrogen, that one, or the hydrogen bonding if there is fluorine attached to hydrogen. So, these things are basically, if these guys, that particular hydrogen will participate in hydrogen bonding, no matter where the hydrogens are. So these guys none of these have OH, none of these have NH, none of these have FH. So hydrogen bonding is ruled out. Next thing we're going to look at is the dipole-dipole. Dipole-dipole is every time there is a more electronegative. So you have to look at which is the more electronegative element that is present. And that more electronegative atom is going to pull the electron cloud towards itself. So it induces the delta charges, so that the more electronegative element will have a delta negative charge, and then the less electronegative atom will have a delta positive charge. But now here it is, even though in this case, let me just make this really tiny. Even in this case, fluorine is delta this is too small. Okay, even though this fluorine has a delta negative, this has a delta negative, this has a delta negative, and this has a delta negative, and this is a delta positive. This chlorine is pulling the electron clouds towards itself. This fluorine is also pulling the electron clouds towards itself. This fluorine is also pulling the electron clouds towards itself, and this one is also pulling. But the overall, the pull or the effect, it cancels out. And when it cancels out, then what happens? This molecule becomes a non-polar molecule. So you're now going to look at all these pieces, whether a molecule is polar or non-polar. So overall, if this is a non-polar molecule, this does not have so this one does not have no dipole. This does not have a dipole. Okay. So even though it has a polar molecule, polar atoms like fluorine, but overall the pull cancels out. And so we have that it's a non-polar molecule. All right, next is the LDF. Now in LDF, sulfur, the electronegativity of sulfur is a little bit higher than the electronegativity of carbon. So there is a charge is induced here. So look at this. What am I saying? Is it correct? So here you see is the sulfur. So that bond, sulfur is 2.5. Oh, sorry, carbon is also 2.5. So carbon and sulfur, so more or less similar, but I think sulfur maybe a little bit, but not that much. So still, so overall, even though, so I'm going to just erase this, it's similar values. So anyways, so with that said, this molecule is also non-polar. Okay, next is, now look at this sulfur. But, as far as I know, there's slight difference in the electronegativity of sulfur and carbon. So slightly different, slightly. So carbon is slightly positive. So, so just keep that in mind that even though there's going to be very little polarity, very small, very, very small polarity here, little bit. It's not like 100% non-polar. It's not that. Okay, very small polarity. But oxygen here on the other one, oxygen is delta negative. Sulfur is delta positive because oxygen is pulling the electron clouds towards itself. Oxygen is more electronegative than sulfur. The electronegativity of oxygen is more than the sulfur. So in that case, now anytime, remember that carbon and carbon will always be non-polar site, always. Anytime you have carbon and hydrogen, okay, carbon and hydrogen, it's always going to be non-polar. So so this side is non-polar, this side is non-polar, and this side is also non-polar. So let's just do this here. Let me put in another color. So here is this is the non-polar end. This is the non-polar end, but this end is the polar end. So the polarity is towards. So there's definitely a dipole in this molecule. So this is a polar molecule. This is polar. This is polar. Okay. The more polar the molecule is, the stronger the particles are going to be attracted. More polar means more intermolecular forces in the particles. So very difficult to break the bond in them to convert them from a liquid to a gas. Now, the last one is all carbon, 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 hydrogen. So all of them are, these guys are all cool, very cool, very cool. Okay, so all of them are basically, so this is a non-polar. So London dispersion is present in all, but so that's kind of ruled out. Next thing is the polarity. So this gun is more polar. So let me get it now in a different color. So this will have a highest boiling point, more intermolecular forces. So this is the highest boiling point. Okay, so boiling point is highest. So this will be the first one, very high, highest boiling point. Very difficult to remove these, then break the network, So that's one thing. That's the next. Next is coming the next one is because the other one has a small polarity. So this is the second, up to the second number. Then this is the third. And this is the fourth. So we also consider not only we consider the dipole. This is an example of dipole interaction. This is one piece, but we also look at the molecular weight. So this has a higher molecular weight. So higher molecular weight or more atoms than CF4. Okay, so that is why it's at the third number. So this is how you will see the decreasing boiling point. So which one is that? So I put the numbers here. Let me just put them in a color. So this is the first one, the top, decrease. So going from here, go next is this one, then is this one, and then then it comes this one. Okay, so that's how it is. All right, next is decreasing arrange in the decreasing boiling point. Now, again, this is an example where you are given, these are the examples from the same group. So these are the same column or the same group. So if you look at it in the same group, you have carbon, then you have you have carbon, and after that comes carbon, then comes silicon, then comes germanium. So these are these examples. Now, obviously, this is, in this case, if we are trying to find a decreasing boiling point, so we are going to look at the molecular weight. So this is an example of the molecular weight. So obviously, decreasing molecular weight. So the one that has the maximum molecular weight is going to be which one? So this is, the size is increasing, right? So the size is increasing as you're going. So carbon is small size, and germanium is a big size. And out of that, germanium chloride is going to be the biggest. So let's write this down here. So GeCl4 is the highest. After that comes the SiCl4. After that comes GeH4. After that comes SiH4. You don't have to calculate and then comes the CH4. So arrange the degree. So this is the smallest boiling point. So this has the smallest boiling point. All right, and this is a solid, so this will have the highest boiling point. Okay, so again, depending, see, chlorine also has a high boiling, chlorine also has a size. So here we are looking at the molecular weight and the boiling point. So keep this in mind that boiling point is directly proportional to the molecular weight, or so when the molecular weight is higher, the boiling point is higher, and when the molecular weight is lower, then the boiling point is also lower. Okay, so that's the direct relationship. All right, next is, which of the following forms the hydrogen bond? So here we are obviously for the hydrogen bond, and they're asking you to draw the structures or look at the structures. So here, this is the C, H3 here, H3, and then you have COOH. Okay, so this is one structure. The next one is nitrogen, lone pairs, just like ammonia. So here is a CH3, the other one is CH3, and then this one is the CH3. Okay, and then comes the other one, fluorine on the top, and then you have, so CH3, sorry. So this is carbon, carbon, and then hydrogen, and hydrogen. Okay, then comes NH3, NH3, hydrogen, and here. So which ones are going to form the of the following, which one will form? So we see that the hydrogen attached to oxygen, this one definitely, very polar bond. So why does it participate? So we'll look into that also. So this is negative. So how does this participate? This piece is the rest of the molecule. So here, so CH3, COOH. Okay, and here you have oxygen, and I'm just going to draw one example, CO, and then CH3. Okay, so here we see one hydrogen has a delta positive. Each hydrogen has a delta positive, but oxygen has a delta negative. This oxygen has a delta negative. So it's always the hydrogen bonding is with the hydrogen of one molecule bonded to the oxygen or nitrogen or fluorine of the neighboring, the one that is near them, neighboring molecule. Okay, so this is the always between the two. So here we see, because this oxygen has a lone pair, this oxygen also has a lone pair. So what is happening? So they are going to lend their lone pair. So let me use a different color. So here this oxygen lends its lone pair to this hydrogen, and this oxygen lends the lone pairs to this hydrogen. And so this is a hydrogen bond, and this is a hydrogen bond. Okay, get it? Let me make this bigger. So this is what happens. When the neighboring oxygen lends its lone pair to the hydrogen of the other neighboring molecule, okay, and this particular hydrogen has to attach to, the oxygen. It's only then it will work, or nitrogen. Okay, so that's one piece. Now, this one doesn't have the possibility of that. This guy doesn't have, so there is no hydrogen bonding here. And similarly, because it does not have an H bond, NH bond needs to be there. NH bond is not present. So therefore, no hydrogen bond here. Next is the CAF. Same is the case. Here also, FH bond is missing. What am I writing? No NH bond. Similarly, no FH bond. So it's always, OH and FH. So here, the other hand is this, the other one will take place. So here there's going to be hydrogen bonding. Okay, no hydrogen bonding in this case. So it's always the hydrogens, because what happens is that in this case, let's look at this one, nitrogen, hydrogen, and this lone pair, and then hydrogen, let's do this here, nitrogen, hydrogen, and this lone pair. So what's happening here? Hydrogen. So in this case, it's always these hydrogens that get unfairly treated. Hydrogen positive, and hydrogen positive, and hydrogen positive, and hydrogen positive. Oxygen, nitrogen delta negative, nitrogen delta negative. But what happens then? In that case, the lone pair is given to this hydrogen. and it's a very weak bond, okay? And then same is the case, this lone pair is given to one of the hydrogens. So that is the hydrogen bond. So it's very important to have that hydrogen present. Okay, it's always a hydrogen of one and oxygen, nitrogen, and the fluorine of the other. Okay, so that's the hydrogen bonding. Then decreasing the boiling point. And once again, since these molecules have weird names, you will not be given the, like, we will give you the structures for the, so like, for example, 2,4-dimethylheptane. So that's the structure. Now, remember, all of the carbon-hydrogen bonds, every time you have carbon-hydrogen, carbon-carbon bonds, so there is always going to be non-polar. Grease, like oil, like wax. Okay, so the question is decreasing boiling point, but the molecular weight, so this is CH2, this is CH2, this is CH, CH2, CH, CH2. So don't worry about it. So this one, the molecular weight is obviously, just looking at it, is very high. Then comes, so when we are talking about the boiling points, we are going to look at the molecular weights also. All of them have London dispersion forces. So that's one thing. So now, molecular weight in this case is neon. So the neon is, the weight of neon is 20 point something. I can see this clearly. 20. Okay, neon is 20 grams per mole. Okay, we'll have to get this weight. Give me 1 minute. Okay, so I got the molecular weights of these, and these are also called, these are the molecular weights, but molecular weights are also called a molar mass. So the units for the molar mass is grams per mole. So this is something you see, even if you do it online, you will see this. Anyway, so here the weight, the decreasing. So here the 119, 70, 76, 20, 128. So obviously we see that so let's put this here. The minimum is this. So arrange in the decreasing. Yeah, so the maximum is this one. So first is this. Second is, 1 second. Second is this one. Then comes the third. Third is this. Fourth is this. And fifth is this. Okay, so this is how you will arrange. But in my personal opinion, I think, in my personal opinion, KBr should be highest, because it is ionic. And ionic bonds are always very high boiling points. So ideally, this should be first, because it's ionic, because of the ionic bonds. Ionic bonds are very difficult to break. Because of ionic bonds, so this one should get the first. So this is first, and then this is the second, because carbon-hydrogen, bonds and carbon-carbon bonds are still like a grease, like a wax. So they should melt easily, like a wax. But I don't know if this exists or as a liquid or what, but anyway, so this one is this is the order. Okay, so decreasing order, the least is the neon, should have the least. Next is identify the most significant force. Now, like I said, the London dispersion forces are present in both the molecules. So London dispersion is in both the molecules. Both of them will have the dipole, because why? Because fluorine is more electronegative. So dipole is present in this. Fluorine electronegativity is higher than hydrogen. So this is the reason why dipole is present. Here also dipole is present, because we will see that the chlorine electronegativity is higher than the hydrogen electronegativity. So as a result, what do you see? You see that next thing is just the London dispersion. The hydrogen bonding. So this has the hydrogen bonding, because, HF, fluorine, 1, 2, 3, 4, 5, 6. Remember, hydrogen bonding, it's always the hydrogen that is attached to fluorine. But in the next case, there is no, it doesn't apply to chlorine. So no hydrogen bonding. Okay, so the most significant one, the identifier, the one that's like distinguishing the two is the hydrogen bond. All right, so that finishes this part. And you need more practice. You should be doing the extra problems. Okay. All right. Thank you for watching. Bye.